try to be succinct, and I don't think I need to introduce too much background, but first, acknowledgements. It takes a village, a big-ass village, so I want to make sure everyone's get there to thank you. So mitochondrial dysfunction, I kind of look at it as cellular engine failure. A lot of us do. Different, I guess, starting points, but in general, what you have is when you've got electrons floating around that escape from the ETC, and you've got oxygen, they form reactive oxygen species. Typically, you have things inside the mitochondria like these antioxidant enzymes, catalase, peroxide dismutase, and glutathione peroxidases that help to buffer the damage. But when you have too much, also you got DNA polymerase that helps repair mitochondrial DNA, and it's got a low error rate. But when you got too much ROS flying around, it damages everything. It damages the mitochondrial DNA, the stuff that's supposed to protect it, the stuff that's supposed to repair it. And so you have this accumulation of mutated mitochondrial DNA as you get older. And so this sort of perpetual dysfunction loop contributes to some pathogenic heteroplasm that we see as we get older. And so in terms of Pac-Man, imagine this is a young cell and an age or disease cell with the ROS as little dots and the antioxidants as little Pac-Man. Mitochondrial dysfunction contributes to oxidative stress, which then is also increases as you get older. And so what we're really trying to see is how can we prevent the game over situation. And so mitochondrial transplantation is a very interesting whatever you want to call it, mitotrans. Is a very interesting modality because it's the perfect care package. You can deliver better DNA repair, better DNA, and also antioxidants all in one package to cells. And from the conference, we know that there are at least 3 well-characterized modalities or methods of transfer. Being first being the tunneling nanotubes, where there's literally a bridge. Encapsulation, and that could be whether it's sort of like isolation of microvesicles or creation of lipid nanoparticles that you can load your mitochondria into, or just the uptake of unmodified or extracellular mitochondria. And so in my work, when I first started looking at transplantation, I was interested in whether we could deliver mitochondria to CD4 T cells. So I'm an immunologist, PhD immunologist by training, and I was interested in the impact of aging on T cell function. And so we were able to establish a simple protocol where we could culture cells, isolate mitochondria, and then through centrifugation we would deliver these cells to CD4 T cells. And we did the initial experiments with some GFP type mitochondria. One, because like Pat said, the dyes leak and reviewers did not like the dyes. So, but anyway, so we were able to show with simple centrifugation that the mitochondria get into the cells, and really just by augmenting the amount of T cells that you had in a 96 well plate versus the amount of mitochondria, you can really modify it to get a more or less 100% efficiency in delivery. And so one of the first things we looked at after transplantation, we're comparing young CD4 T cells, old CD4 T cells, and old plus mito. We used the Seahorse assay to measure oxygen consumption. We saw that compared to the old and the young, the old plus mito had a significant increase in oxygen consumption. All the parameters that we looked at primarily mitochondrial superoxide production using electron paramagnetic resonance, which is like one of the most sensitive ways to do it. We saw after transplantation that mitochondrial ROS went down, so better oxygen consumption, lower smoke coming out of the exhaust pipe. We did some proteomics. And then we did go ontology analysis, and some of the most upregulated pathways were related to the microse complex, cristae formation, and so we followed that up by looking at transmission electron microscopy. And from the images, you can see that the old CD4 T cells, these are the mitochondria, and then these are the new and improved mitochondria. This is only 4 hours after transplantation. And so in T cells. For those of you that are not immunologists, if you compare the response of a young CD4 T cell versus an old CD4 T cell that's responding to the same cognate antigen, typically the older T cell will display lower markers of activation, it will produce lower amounts of cytokines with a bias towards pro-inflammatory cytokine production, and they don't proliferate to the same magnitude. So the question was simple. Because T cells have, the function of T cells depend on mitochondrial signaling, if we couldn't deliver younger mitochondria or healthier mitochondria to these HT cells, would that have an impact on their ability to activate, produce cytokines, and proliferate? And the short answer is yeah. So T cell activation went up, indicative by CD69 and CD25. And this is again just comparing old CD4 to old CD4 plus mito. So it's a paired experiment. We looked at IL-2 production, which goes down with aging, and simple act of delivering younger mitochondria led to improved IL-2 production, and then proliferation also improved in these T cells. So this was all ex vivo, and we also did some in vivo experiments where we looked at two different pathogens, one a virus and one non-viral. For influenza, we looked at mortality primarily, and then for tuberculosis, we looked at COV burden, mycobacterial burden in lung and spleen after 21 days of infection. So again, we took 90 CD4 T cells, came from the same mice. Some got mitotransfer or mitotransplantation, and then some just got vibes, and then we tracked them. So here's the influenza data. We saw that the mice, these are rat knockout mice, by the way, that received the O plus mito CD4 T cells, they had the best survival compared to the mice that received old 90 CD4 T cells, or the mice that didn't get anything at all. When we looked at MTB burden in the lung and spleen, we saw that the mice that got the right knockout mice that got the O plus mito group had the lower mycobacterial burden. So there was a question earlier about mitochondria and senescence. I'm not an expert on senescence, but I know that it's involved in T cell exhaustion and T cell senescence. Ultimately different phenotypes, but both of them are mediated by mitochondrial dysfunction. And in tuberculosis, you tend to have a lot of exhausted cells the longer the infection persists. And so we did this, we set up a second experiment where we would take TCR knockout mice. So these mice don't have a T cell response. And we would now take, again, these mitotransferred T cells and deliver them to TCR knockout and phenotype them at 30 and 60 days post infection with tuberculosis. And long story short, we saw some reduction in exhaustion-associated CD4 T cells in the lung and spleen. And so suggesting that it could have a lasting phenotype. And this is only after one round of transplantation. We went a little further, we took some elderly CD4 T cells, average age of the donors was 65, and then just gave them mitochondria from fibroblasts. And then we, for this experiment particularly, we stimulated the cells for continuously for seven days to sort of mimic the pressures of exhaustion. And what we saw is that even in these situations, we saw that the O plus mito, or the elderly CD4 T cells with mitotransfer, had better activation and lower markers of exhaustion. We then took a look at senescence, briefly, just in this model, just a single stimulation for 3 days, and then we just phenotyped the cells. And again, better activation, lower markers of exhaustion. We also did some proteomics. It's in the paper listed on the bottom. You can take a look. And so, a quick summary of just this stuff. Transplantation increased OXPHOS, reduced oxidative stress, and increased the crystal density. It improved T cell activation, cytokine production, and T cell proliferation. It extended survival of mice with influenza infection, and then it reduced the mycobacterial burden in mice. All of this is great, and I got excited because I'm interested in the immune cardiovascular axis. If this is enough, regardless of what the nitty-gritty mechanisms are, if this works for T cells, then for all other cells that use mitochondria as a signaling modality, why not try it out? And I did for a while. I was trying it in all these different cell types, but this comes to the crux of the problem. So for mitochondrial transplantation right now, in most published work, it's a very low efficiency. It has a low transfer efficiency. So for example, in here, 10 to the 1 is just 10%, and in these studies, it's around 40%. To me, that's low. And even if you can take some cells out of the body, like for the immune cells, and augment it to get to 100%, you really can't do that for cells in the body that you can't take out of the body, like endothelial cells. And so, as in being part of a cardiovascular group, we're interested in targeting the endothelium because it's one of the first layers. It's the outermost layer in blood vessels, and it's the first to erode in a lot of cardiovascular diseases. And so, I just think that right now it's not practical to do transplantation on a large scale for for these diseases. And so I kind of compare it to the bus system right now, where in a lot of studies where we're doing, and again, I'm not throwing shots at anybody, this is just the reality. It's, we're doing systemic injections and seeing where the mitochondria go in clear and present danger, and that's good. But I kind of want to get to more of like an Uber approach where we can actually tell the mitochondria where to go, because targeting is ultimately going to lead to, I think, better results. And so I took some ideas from the ADCs from the cancer space. So ADCs are antibody-drug conjugates, and the beauty of them is that a drug enters the cell because of the sort of receptor-specific antibody interaction that occurs on the surface. Drug gets internalized, and then boom, the cancer cell apoptosis. And so start playing with the idea of making something similar for mitochondria, where instead of trying to encapsulate it, why not attach antibodies to the outside of the outer membrane? And so we're going to call these antibody mitochondrial conjugates or mitotags. And so again, I don't have this proven, but I'm naive in thinking that maybe it's just a receptor-mediated intake that would lead to internalization of mitochondria and bioengineering programming. And so we came up again with a simple protocol where we could culture donor cells with a little secret seasoning, isolate these mitochondria that are amenable to complex human antibodies, and then create these mitotags. And so because the mitotags or the antibodies can have fluorescent tags on them, I don't have to worry about the eyes too much. And so we made one that's specific to endothelial cells based off of anti-CD31 or the PCAM receptor that has a P fluorophore. So you can easily track them by confocal. And so here's the endothelial cell, the P cadherin on the surface, the nucleus, and then the mitotags inside. Proof of principle. So here's another experiment using mitotracker deep red in the gray, and the localization of the roughly 80% localization of the delivered mitochondria by mitotag system. And here's another experiment showing the comparison of the unmodified, or I like to call them the naked mitos versus the mitotags. And it leads to a roughly, at least in this experiment, it was a roughly, at the low end it was a 10, and then to the higher ends 50 times more deposition of mitochondria. And so for this, to show that there's functionality with the mitotags, we did actually specificity first. So we did this experiment where we took cells, simple co-culture of cells that have CD31 expression, endothelial cells, and then cells that don't have CD31. So in this case, we used vascular stem cells, 50-50 culture, sprinkled the mitotags on them, and then we looked to see whether there was specificity just for the ECs or not. And so we've got the endothelial cells in the translucent, almost gray, the vascular stem in the green, and then the mitotags are primarily localizing or being internalized by the endothelial cells. So it suggests that there's specificity. Then we also did sort of like a parallel flow cytometry experiment to actually quantify how many endothelial cells had the mitotags, and then we also saw some of the vascular stem cells with mitotags in them. It could be true nanotunneling to be determined. So another experiment that we did to test out the potential of mitotags in sort of like an inflammatory condition. So we stimulated endothelial cells for 24 hours in interferon gamma, sprinkled the mitotags, and then 24 hours later we looked at ROS analysis, ROS readout by flow. And so here we see that in the left are the cells that got nothing, no interferon gamma, and then in the middle are the cells that just got interferon gamma, and then interferon plus mitotags, and we saw that there's a reduction in oxidative stress. So suggests that there's functional benefit to using the mitotag system, and the mitochondria are functional. Did another experiment to look at retention, because that's always a big question anytime I talk about transplantation. So row cells don't have functional or active mitochondrial DNA. Regular cells do, and so the idea is, if we can deliver, if we can use the deliver mitochondria via the mitotag system to row cells, and they continue proliferating, then that would suggest that one, OXPHOS is rescued. One, because OXPHOS is necessary for production of uridine, and so if you don't have OXPHOS, you got to supplement the cells with uridine. So what we did is we took row cells, added the mitotags, row cells without the mitotags. Both of these don't have any uridine supplementation, and then these are the cells that got uridine. And so we're seeing that to some extent, and this is not like ultra optimized experiment. It's just YOLO. But what we're seeing is that the mitotags are rescuing, to some extent, proliferation of these row cells that didn't have mitochondria. I only tracked them in this experiment for up to 12 days because I have to go places, but I left the cultures growing. And so these are the cells that they look at. These are the mitochondria of the cells that they look at 30 days. And so these are the row cells. Without yearly supplementation, they tend to become enlarged. And then over here on the right, at 30 days, they don't really look normal per se, but they're growing. And so we'll see, it's been roughly 90 days, and so we'll see when I get back if I can do some isolate mitochondrial DNA, look at the oxygen consumption, these other things. But anyway, so with this system, what I think, I know it's happening. We have now the ability to, we already had the ability to manipulate the nuclear genome through CRISPR and other nuclear genetic engineering modalities, but now it's also possible to, I think, on a higher scale, manipulate mitochondrial DNA extracellularly and manipulate mitochondrial cells extracellularly, deliver them to cells at a high enough quantity to induce biogenetic reprogramming and ultimately cellular reprogramming. And so some of the future goals is to really make a sort of a mitotype repository for different tissues and different cell types. And honestly, I like transplantation, the possibility of using mitotypes to treat really any condition that is afflicted or contributes to mitochondrial dysfunction. So for example, immune aging, since I'm an immunologist and I'm biased, I'm going to show some more stuff about that. Creating a different mitotype that's specific to immune cells, because the idea is, as long as the receptor does rapid endocytosis, we can co-opt it and deliver mitochondria to them. And so CD11A is one of those receptors expressed on all immune cells. And so we made a CD11A mitotype for immune cells. And so here we have some graphs comparing the uptake of naked mitochondria versus the mitotypes on a mitochondrial volume dependent, sort of dosing dependent grading. And we see that even at the lowest levels, 60% is better than anything I saw published, other than my papers. 2 minutes, okay. Anyway, so I think this is a great way of delivering mitochondrial cells with a lot more efficiency and targetability. And so I'm going right now, thank you to the borrowers, because they're allowing me to really do some bioengineering experiments to generate the repository and really customize mitochondria to augment the processes to see how they might impact cells. We've got another project with funded by AHA to look at whether the mitotypes can help in diverting or reducing endothelial dysfunction and macrophage inflammatory profiles in aneurysm development. We've got experiments with NASA. Right now we're going to develop a mitotype system for hopefully astronauts to take up to space. That's my collaborator, Robert. And then we've got another experiment that's going to take the mitotypes into H marmosets to see whether it actually has an impact on systemic inflammation and immune cell activity. And if you want to collaborate, hit my line, because I definitely want to collaborate. With that, I'll take questions.
Thank you so much for the presentation. So now we have time for one question from the audience.
I'm from SUNY Buffalo. We are also endothelial cell biologists interested in horizontal transfer of mitochondria. But we use extracellular vesicles. We found that endothelial cells release mitochondria in these EVs at a high rate. Why, could you try to convince me why in an endothelial cell model, why I should switch to mitotags rather than rely on this endogenous system where endothelial cells already release mitochondria?
I mean, if you like to do a lot of work and you want to isolate a lot of microvesicles, then I'm not going to stop you. That's just it. I'm not that guy. So this system, one, especially because endothelial cells are probably releasing mitochondrial vesicles. This could act like as a port system. So instead of having to deliver mitochondria to every cell type, you could have targeted delivery just endothelial. They can repackage them, because we're not smarter than Mother Nature, and I'm not trying to work harder than Mother Nature either. So they go repackage them and have the body communicate. Or, again, because the system is customizable, whatever cell type you wanted to deliver them to, if you wanted to deliver senescent mitochondria to healthy cells to see what happens, you could do that. If you wanted to deliver pluripotent mitochondria to cancer cells, you could do that. I don't think I need to convince you. You need to convince yourself.
I'd like to thank you for convincing the audience with your brilliant response.
Pardon?
That was a brilliant response.
Oh, yeah.
And another question. Do you know what happens with this larger mitochondria? Do they get along, or they match, they don't match, and you have to see what happens like several days after they do so much mitochondria inside them?
So what happens after the cells, so from in the TILSA experiments, we've done some cool, it looks like they're co-localizing. Every time I've done transplantation, long term, what I actually see is a decrease in mitochondrial mass, and I suspect it's the same thing occurring here. Whether the new mitochondria are staying forever, I'm not sure yet. But at least in the row zero model, it suggests that there's like lasting power or lasting potential, because the cells can't divide without uridine, and if they're still dividing with the mitochondria I just gave them, I mean, the math's mathing.
So here's a question, because since yesterday I was thinking like why nobody's speaking about the astronauts. You are the one who brought that. So
Oh,
really
thank you.
I've seen some videos in YouTube before, like coming to this. I was reading also. So my question is like, what aspect like they are taking the mitochondria along with them? So you can better answer that question. And then in the lab, have you ever thought like while working, so let me take some mitochondria and reduce my age, and then get another publication and increase my muscular capacity and the regular work. Did you ever think of that?
If I did, I probably would not incriminate myself with that kind of shine. But no, I haven't done that yet. As far as the NASA project, so we got funded through the NIAC system, and it's essentially, so if you leave Earth, if you want to go to Mars, there's a lot of cosmic radiation. Damages the nuclear compartment, but the accumulation of damage in mitochondrial DNA is a lot faster, and so the phenotypes pop up a lot sooner. And so there's been now ample evidence of multi-organ mitochondrial dysfunction in astronauts and animal models. The idea is that we're essentially trying to build like a black box or like a mito-shielded box that you can take to space and have these sort of enriched mitochondria that have added antioxidants and added repair enzymes that astronauts can then infuse, and the longer they go out to space, the more sort of refueling they can have. If that makes sense.
Okay. Thanks so much.